Difference and sum of two cubes identities, further solved problems. Problem 12. Use the difference of two cubes identity to solve x cubed equals 8, where x is a real number. We have to solve the equation x cubed equals 8 using the difference of two cubes identity, but at the moment we don't have any cubes on the right-hand side and we don't have a difference of two cubes. But it's easy to rewrite this equation so that we do. First of all, we can say that x cubed equals 8 is equivalent to the equation x cubed equals 2 cubed, and that's equivalent to the equation x cubed minus 2 cubed equals 0. And now we can use the difference of two cubes factorization to write x minus 2 times x squared plus x times 2 plus 2 squared equals 0, which simplifies to x minus 2 times x squared plus 2x plus 4 equals 0. Now note that I have been using this symbol, the equivalence symbol, in each of these transformations. I've been using that because x cubed equals 8 can be turned into x cubed equals 2 cubed, but similarly we can turn x cubed equals 2 cubed back into x cubed equals 8. We can also do the same thing for x cubed minus 2 cubed equals 0. We can turn that back into x cubed equals 2 cubed. And in fact, each of the transformations that I've made as I've been working through this simplification or factorization are reversible. That means that the equation x cubed equals 8 is equivalent to, i.e. has the same solutions as, the equation x minus 2 times x squared plus 2x plus 4 equals 0. So if I find the solutions to this equation, I also have found the solutions to this equation. We now recall the following important fact, which is if a and b are real numbers, then if a times b equals 0, then it must be the case that either a equals 0 or b equals 0, or both, in fact. So bearing that in mind, the equation x minus 2 times x squared plus 2x plus 4 equals 0 is equivalent to x minus 2 equals 0 or x squared plus 2x plus 4 equals 0. Now in the case of x minus 2 equals 0, we can immediately solve to give us x minus 2 equals 0 implies x equals 2. In fact, that's an equivalence. So we have one solution from x minus 2 equals 0. The question is, do we get any further solutions from x squared plus 2x plus 4 equals 0, bearing in mind that x must be a real number? Well, it turns out that in fact x squared plus 2x plus 4 equals 0 does not have any real solutions, and we're going to show that in two ways. First of all, we're going to look at the discriminant of a quadratic, and the discriminant of a quadratic is the quantity b squared minus 4ac, where the quadratic we're interested in is ax squared plus bx plus c, and the quadratic equation that we're interested in is ax squared plus bx plus c equals 0. Now that equation, ax squared plus bx plus c equals 0, only has real solutions when b squared minus 4ac, which is called the discriminant and given the symbol delta, is greater than or equal to 0. Now, the equation we're interested in is x squared plus 2x plus 4 equals 0, and that gives us a is 1, b is 2, c is 4, from which we can compute the discriminant delta, b squared minus 4ac, as 2 squared minus 4 times 1 times 4, which is 4 minus 16, which is minus 12, which is less than 0. Thus, x squared plus 2x plus 4 equals 0 has no real solutions. Geometrically, this corresponds to the fact that the graph of y equals x squared plus 2x equals 4, which you can see drawn here, does not cross the x-axis. We're interested in whether x squared plus 2x plus 4 can equal 0, and in fact we're going to show that x squared plus 2x plus 4 is greater than 0, strictly greater than 0, by the method of completing the square. Now, to complete the square, you consider an expression of the form x squared plus px, which can be rewritten as a perfect square, x plus p over 2 all squared, minus p over 2 all squared. So when we rewrite x squared plus 2x plus 4 in completed square form, we get x plus 1 all squared minus 1 squared from the first two terms, plus 4 from the remaining term there, and this simplifies to x plus 1 all squared plus 3. But immediately we can see that this must be strictly greater than 0, because x plus 1 all squared is a real number squared, which cannot be negative. Plus 3 is positive, so we are adding a non-negative number to a positive number, so the result must be strictly greater than 0. So x squared plus 2x plus 4 is strictly greater than 0, i.e. it cannot be 0. So to summarize, we showed that x cubed equals 8 is equivalent to x minus 2 equals 0, or x squared plus 2x plus 4 equals 0, and we're interested in solutions where x is a real number. And that is equivalent to x equals 2, but no further solutions from x squared plus 2x plus 4 equals 0. So the only real valued solution to this equation is x equals 2. Problem 13. Show that a cubed equals b cubed implies a equals b if a and b are both real numbers. To solve this problem, we use the same technique as we used in question 12. We have that a cubed equals b cubed implies a cubed minus b cubed equals 0, and here we have the difference of two cubes, which we can factorize into a minus b times a squared plus ab plus b squared, which must be equal to 0. From this, we can say that either a minus b equals 0, from which it follows that a equals b, or a squared plus ab plus b squared equals 0. We now rewrite the expression a squared plus ab plus b squared in completed square form. If we take the first two terms a squared plus ab, we can rewrite them as a plus b over 2 all squared minus b over 2 all squared, and we have the final term plus b squared, which simplifies to a plus b over 2 all squared plus 3b squared over 4, which equals 0. Now the question is, can a squared plus ab plus b squared, which equals this expression, ever equal 0 for any values of a and b? To find out, we apply this key fact. If x is a real number, then x squared is greater than or equal to 0, and x squared equals 0 only when x equals 0. So in order for this expression to equal 0, then this term and this term must both separately be 0, i.e. a plus b squared over 2 must equal 0, and simultaneously 3b squared over 4 must equal 0. It then follows from this fact that a plus b over 2 must be 0, which tells us that a equals minus b over 2, and that b equals 0. So from this fact, we can say that a must equal minus 0 over 2, which is 0. So we have shown that a squared plus ab plus b squared equals 0 implies that a equals b and that they both equal 0. Now, we've already shown that a cubed equals b cubed means that a minus b times a squared plus ab plus b squared equals 0. And from the first term, we have that a equals b, and from the second term, we have that a equals b, but they both equal 0. But in both cases, a must equal b. So in total, we have shown that a cubed equals b cubed implies a equals b as required. And from this result, it immediately follows that if x cubed equals a cubed, which is equivalent to x cubed minus a cubed equals 0, then x must equal a if x is real. And similarly, if x cubed plus a cubed equals 0, which is equivalent to x cubed minus a all cubed equals 0, implies that x equals minus a as long as x is real. So, for example, if x cubed equals 8, then x cubed equals 2 cubed, so immediately we can say that x equals 2. And if x cubed plus 8 equals 0, so that x cubed plus 2 cubed equals 0, then immediately we can say that x equals minus 2, as long as we're only talking about real x. Problem 14. Find x cubed minus 1 over x cubed, given that x minus 1 over x equals 10. We have that x cubed minus 1 over x cubed equals x cubed minus 1 over x all cubed, which is the difference of two cubes, which we can factorize as x minus 1 over x times x squared plus x times 1 over x plus 1 over x all squared, which simplifies to x minus 1 over x times x squared plus 1 over x squared. And so we already have the x minus 1 over x expression that we need there, and we now need to express x squared plus 1 over x squared, this bit, in terms of x minus 1 over x. Now, given that we have to produce terms of the form x squared and 1 over x squared, the obvious thing to do is to look at x minus 1 over x all squared, because that will produce those terms. So if we expand it as x minus 1 over x times x minus 1 over x, we get x squared minus x times 1 over x minus 1 over x times x plus 1 over x all squared, as you can see if we look at the crab clause expansion. Now this simplifies to x squared minus 2 plus 1 over x squared. And so we have our x squared and our 1 over x squared, but we've got minus 2 instead of plus 1, which we have to rectify. But it's easy to see that we can turn this expression into this expression by adding 3. So if we do so, on the left-hand side, we get x minus 1 over x all squared plus 3 equals x squared plus 1 over x squared. And so finally, we have x cubed minus 1 over x cubed, which, remember, was x minus 1 over x times x squared plus 1 over x squared, becomes x minus 1 over x times x squared minus 1 over x all squared plus 3, which is what this expression turned into. And now we can substitute 10 into the right-hand side to get 10 times 10 squared plus 3, which equals 10 times 103, which equals 1030.